Hello and welcome to this presentation related to analysis of struts. In other words, we're going to analyse members that are in compression. The members we're going to analyse are considered to be slender and thus can be subject to buckling failure. The right hand sketch here shows a platform supported by two stanchions. These are effectively struts or compression members. The upper end of the stanchion is attached to the platform by two bolts, and the lower end of the stanchion is attached to the retaining wall here by again two bolts. The loading shown here from the platform puts the member into compression, so it's analysed as a strut. The diagrammatic view of a compression member here shows a strut in a horizontal position this time with force P applied at its ends. This configuration shown here is actually a pin-ended strut, and we'll discuss the various fixates of struts as the presentation unfolds. This presentation is just used an illustration of how to analyse compression members using a standard procedure and makes reference to standards that are now superseded. So obviously, if analysing struts within industry, you will need to refer to the current standards or codes of practice. Here's a presentation overview related to analysis of struts. That's compression members subject to buckling. Presentation commences with a general introduction outlining various compression members, practical situations, and where checks for stability or buckling considerations are required. The introduction continues with some definitions. We define the applied axial loading to our struts, symbol P, the radius of gyration, symbol lowercase k, slenderness ratio, Greek symbol lambda, allowable compressive stress, Greek symbol lowercase sigma, the effect of end fixity on our various struts, and we introduce the concept of effective lengths, designated L suffix E. We consider example 1, where we calculate slenderness ratios of two different struts, where the slenderness ratio, symbol lambda, is defined as the effective length divided by the least radius of gyration. We then consider exercise 1, which requires us to calculate the slenderness ratios of various struts, given specified parameters. Next, we consider the general procedure for the sizing of universal columns, subject to an applied compressive force P. Example 2 is a practical illustration of how to size a universal column using our general procedure when we're given the applied load P and the actual length of the column or strut L. Exercise 2 requires us to size a universal column in line with the solution procedure of example 2. Finally, there's an array of questions for us to undertake at our own pace. And here are the approximate timings related to the commencement of the various sections within the presentation to hopefully aid your ease of access through the presentation. But as always, these are only approximate timings. Here's a brief introduction. In previous presentations, we have calculated the axial stresses or direct stresses in members, their in tension or compression. We have calculated deflections in axial members and also in beams due to loading applied. And in this presentation, we're going to consider compression members where buckling is a failure mode. So essentially, when analysing structural members, there are three considerations, sometimes referred to as the 3S rule. That is, calculate the strengths of the member, in other words, calculate the stresses, tension or compression in the member, consider the stiffness of the member, that's usually undertaken by calculating deflections. Finally, consider stability issues, in other words, check the member for buckling. So in this presentation, it's the third S we're going to consider, buckling of struts. Considering a chair, for example, our weight force acting down places the legs of the chair here in compression. But in this particular case, we're unlikely to be concerned about buckling of the chair because usually chair legs are quite stocky or can be braced as shown here. So buckling considerations of the chair legs are unlikely to occur. Reduction continued again. Here are structural members. These are actually circular sections shown here in the photograph. And if loaded in compression, they could in theory buckle to this kind of shape here. So in this particular situation, they'll be checked for strength to ensure that the axial stresses are not excessive. Let's see the yield point. They may well be checked for stiffness and the deflections that occur due to loading applied. And now they could be checked for stability to make sure they don't buckle if the load applied is compressive. With structures such as electricity pylons, we often use bracing effects to help reduce buckling considerations. Again, members need to be checked that if they're in compression, they do not buckle. Here are two designs I was involved with when employed as a junior design draftsman many years ago. On the left-hand side, we have a platform that's supported by two what are termed stanchions. Shown here, they're actually rolled steel channel sections, and they had to be checked to ensure they didn't buckle under the compressive load from the platform. And here on the right hand side, this is actually a lifting frame, again constructed of two rolled steel channels secured together. What you notice here is that due to the configuration of the lifting cables and the applied load, 100 kilonewtons it shows there, that the channels were actually subject to a compressive load, which meant that the channels had to be analysed not only for the compressive stresses, but also for potential buckling considerations. So here are two designs that involve members that need to be checked for buckling. Another illustration on the left hand side here of a tower and platform actually used to service the valves at the top of these large storage tanks. This is a detailed design I was involved with many years ago, and again the various members that were in the lattice structure of the tower had to be checked for buckling when subject to compressive loading. And finally, on the left hand side of the slide, note that the upper wing skin of an aircraft is predominantly designed for buckling because in general flight conditions the upper wing skin is in compression. So the various members within the structure are subject to compressive loading. So just a few brief illustrations of where compression members in structures, often referred to as struts, occur and where the buckling mode of failure has to be considered. Just for reference, here are the unity brackets that will be required for some of the conversions within these calculations. We'll note that the British standards we're referring to still use centimetres for some of the dimensions and some of the properties of the section, so we'll need to convert, for example, centimetres into millimetres. I've shown the appropriate unity bracket here. We've reviewed unity brackets in a separate presentation. Always remember that they are cancelling unity brackets, so the centimetres have cancelled to leave the millimetres in this first calculation. That was converting a linear dimension from centimetres to millimetres. We will also need to convert an area in centimetres squared to an area in millimetres squared for our calculations. And again, I've used the appropriate unity bracket. Notice it's squared here because we're considering a squared unit. There are many types of compression member. For example, columns in pillars, posts, and stanchions. Columns in pillars are usually made from concrete or brick, stone, and steel. The term posts usually relate to compression members made of timber, and stanchions and struts usually are made from rolled steel sections such as universal columns, rolled steel joists, rolled steel channels, etc. And what all these members have in common is that they are subject to axial loading. As shown in the diagram, the force P or load P is applied to the, in this case, the stanchions. Introduction continued. So let's define some terms. Axial loading, P, is the load that's assumed to act through the centre of the section. And note that rolled steel I sections have different sections than those used for beams, and are often termed universal columns, UCs. Here's an illustration of a universal column, and the applied load in P is assumed to act at the centre of the section shown here. Let's consider the radius of gyration, usually denoted as lowercase k. So the radius of gyration is defined as k is equal to the square root of I divided by a. Let's call that equation 1 for reference, where I is the second moment of area. That's a geometrical property we reviewed in a previous presentation related to beams and bending. And A is the cross-sectional area of our compression member. Now there will be two principal second moments of area, I, and both must be considered when evaluating the radius of gyration. And the two principal second moments of area would be about the x-x axis shown here or the y-y axis shown here. So the radius of gyration values can be calculated from equation 1 above, or they can be directly read from appropriate section property tables. And within this presentation, I'll refer to British Standard 4 tables. Please note that the tables used in this presentation are superseded, and obviously if undertaking this analysis in industry, you would need to refer to the currently approved standards. Introduction continued. Let's define slenderness ratio, Greek symbol lambda. So slenderness ratio of a stanchion or a strut is one of the parameters required when sizing a member. So slenderness ratio is defined as the effective length of a member, denoted L suffix E, divided by the least radius of gyration, symbol K. Call that equation 2 for reference. So for standard universal columns, stated in table 3 of our notes, I'll show you the table on the next slide in a moment, the least radius of gyration, symbol K, occurs about the YY neutral axis of bending. So in other words, about this axis here. So here's the extract from table 3 in our notes related to universal columns. This actually relates to BS4 Part 1 1980, so superseded standard now. So as I said previously, if you're undertaking such analysis within industry, obviously ensure you're using the up-to-date standards. Notice the layout of the British Standard here. We have designation, which relates to the serial size of our universal column. So considering the first section here, it's a 254 by 254 millimeter section. We have the mass per meter in kilograms shown here, 167 kilograms per meter in this particular case. Notice that the serial size relates to the B and D dimensions. It's very generic there. The actual depth D in millimeters and the width B millimeters are stated in these columns. Then we have the thickness of the web, lowercase t, thickness of the flanges, uppercase T. Here's the universal column nomenclature, the depth of the section D, the width of the section B, and here's what's termed the web thickness, lowercase t, and then the flange thickness, uppercase T. Notice the thicknesses are in millimeters here, the actual dimensions for our particular designation. The next column contains the area of the cross section. Notice that's in centimeters squared here, is the value for our section. The next two columns relate to the moment of inertia. That's basically the second moment of area, or the I value. And we have the I value about the x-axis in centimeters to the 4 and about the y-axis in centimeters to the 4. Now what we're particularly interested in from this table is the radius of gyration, symbol k of course, and again we have that about the x and the y-axis. Notice the radius of gyrations are stated in centimeters here. So for our particular section, those would be the values. So those are the typical properties we obtain from, in this case, BS4. Introduction continued. Let's consider the allowable compressive stress, sigma. So table 2 of our notes contains the British Standard recommendations for the allowable compressive stress in compression members such as struts as a function of increasing slenderness ratio. I'll show you this table on the next slide. So here's table 2 from our notes. This tabulates the allowable compressive stress values for grade 43 steel. This is a superseded specification of structural steel. We're just using this for academic purposes to illustrate the process involved with analysing struts. This extract is actually from BS 5950 Part 1, 1985. So it's a superseded standard again, but obviously if undertaking the analysis in industry, you will refer to the current appropriate standards. On the left-hand column, we have the slenderness ratio, lambda, which is dimensionless, of course. In the second column here, we have the allowable stress, sigma, stated in newtons per millimeter squared, or of course that could be meganewtons per meter squared or megapascals. But notice the allowable stresses relate to a flange thickness, capital T, shown here on the diagram, of up to 60 millimeters. So as long as the capital T dimension for our particular universal column or section is no greater than 60 millimeters, these would be allowable stresses for our particular section. So for example, for a slenderness ratio of 30, the allowable compressive stress, if the flange thickness is no greater than 60 millimeters, is 262 newtons per millimeter squared. The next column has allowable stresses, but this time for a flange thickness, capital T, of 17 to 40 millimeters. And the final column again, allowable stress for a flange thickness, capital T, from 41 to 100 millimeters. So the table commences with a slenderness ratio of 20, and as you can see, ends with a slenderness ratio of 300. And obviously you can clearly see that the allowable compressive stress reduces for all values of capital T as the slenderness ratio increases. Typically, at 30 slenderness ratio for our section, we have 262 newtons per millimeter squared. At a slenderness ratio of 80, it reduces to 181 newtons per millimeter squared. And at a slenderness ratio of 120, it's now down to 108 newtons per millimeter squared. So that's our allowable compressive stress table for grade 43 steel. Introduction continued. Let's now consider the effect of fixity at the ends of our compression members. On the following slide, there are 4 column configurations, all having the same length L, but they have varying end conditions. The end conditions affect the critical load under which the strut compression member will buckle, and this end condition effect is applied using what's termed the strut's effective length, denoted as L suffix E, where the effective length is considered to be that portion of the strut over which buckling may occur. This is illustrated on the following slide. So here's table 1 from our notes relating to the effective column length, LE. So in the first column here, the configuration relates to both ends of our strut being pin jointed. So in this case, end A and end B are fixed in direction but free to rotate. In other words, fixed in translation but free in rotation. And the standard states that the effective length for this configuration LE is equal to the actual length. So if our actual length of our strut was 2 meters, for example, then the effective length would be 2 meters. The second configuration is when both ends are direction fixed. In other words, ends A and B of our strut here are fixed in translation and rotation. And we're informed that the effective length now is 0.7 L. So if our actual length of the strut was 2 meters, then the effective length would be 0.7 times 2, will be 1.4 meters in our calculations. Third configuration, one end direction fixed and one end free. So in this configuration, end A is fixed in translation and rotation, but end B is free to translate and rotate. The effective length now is stated as twice the actual length. So again, if our actual length of the strut was 2 meters, then the effective length in our analysis would be 4 meters. And the final configuration we're given in the standard is when one end is direction fixed and one end is pinned. So in this scenario, end A is completely fixed, in other words, no translation or rotation, but end B is fixed in translation, but we can have rotation. The effective length is now 0.85, the original length. So if our actual length again was 2 meters, then the effective length is 0.85 times 2 meters, so it's 1.7 meters for our analysis purposes. So there's our 4 types of configuration we will use within the work we're going to consider. Just to illustrate how to consider the fixities of struts in industrial situations, here's a design I was involved with many years ago as a junior design engineer. And we're essentially designing this stanchion here, which is actually made from a rolled steel channel section. And there were 2 of these stanchions, these struts, supporting this platform here. And from appropriate standards, we were able to work out what the loading was to be applied to the platform from service use, and which we shared equally between the 2 stanchions. The context here was these were platforms that engineers would use to service valves at the top of storage tanks in a very large chemical facility. The attachment of the stanchions at the top here and the bottom here was by 2 M12 bolts. For the compressive load P, we now have to design a stanchion, so that means of course we need to choose the appropriate end fixity. So what would we consider the end fixities to be for our stanchion? Would we consider the stanchion to be pinned at both ends, in other words fixed in translation but free in rotation? That would give an effective length of 1. That may be deemed reasonable because we only have 2 bolts at either end, so the fixations may be limited and some degree of rotation may occur. Or could it be this scenario where we're fixed at the base in both translation and rotation, but we're fixed in translation and free in rotation at B, top of our stanchion? That would allow us to use an effective length of 0.85 of L. So essentially the column would be stiffer as the effective length is lower. Or could we use this scenario? Could we say that because the top of the stanchion is connected to a platform that's free to actually move to some degree, that we have the bottom fully fixed in translation and rotation, but the top is actually free to move in both translation and rotation? Now our effective length would be twice the actual length, so that would consider the stanchion to be very slender. So can you see from that simple example alone that our choice of fixity will have a significant impact on the analysis we're going to undertake. I sometimes refer to this as the art of engineering, and it's for the engineer to make and indeed justify the choice of the appropriate end fixity. Let's consider example 1. Here a stanchion, a strut, has a length of 4.8 meters and is made from a 305 millimeters by 305 millimeters by 158 kilogram per meter universal column. We're asked to determine the slenderness ratio of the stanchion or strut if the following are assumed. A, the strut is pinned at both ends, and B, the strut is pinned at one end and fixed in direction at the other. Now here's our solution work for us here. So the actual column length, L, is 4.8 meters. I've converted that into millimeters here, 4,800 millimeters. Designated serial size here, 305 millimeters by 305 by 158 kilograms per meter. So from table 3 in our notes, I'll show you on the next slide, the least radius of gyration, K, is 7.89 centimeters, and of course that's equivalent to 78.9 millimeters. So this will be table 3 of our notes. It's the universal columns here. Extract from BS4 Part 1, 1980. Designation of 305 by 305 by 158 kilograms per meter. So now we need to read along the row here till we get to the radius of gyration column. And there are two values for radius of gyration. We've got one about the x-x axis here of 13.9 centimeters. But the one we're interested in is about the y-y axis, and that's the 7.89 centimeters. So that's the least radius of gyration for our particular section. Now for part A, we can evaluate the effective length, LE, both ends pinned. The effective length from our table is 1. From our table, both ends pin jointed. In other words, fixed in translation but free in rotation at both ends. The effective length is 1. So the effective length here is simply going to be the actual length of the strut. That's 4,800 millimeters. So our slenderness ratio, lambda, is the effective length divided by the least radius of gyration. Inserting the values. The slenderness ratio is 61. If we now consider part B of example 1, this is now the configuration where we have one end pinned and one end fully fixed. So from our previous table, the effective length for this configuration LE is 0.85 the actual length. From our table, one end direction fixed, one end pinned. In other words, one end fully fixed, fixed in translation and rotation, and one end fixed in translation but free in rotation. The effective length is 0.85, the actual length. So 0.85 multiplied by the 4,800 length calculates to an effective length of 4,080 millimeters. So our revised slenderness ratio, lambda LE divided by K, the effective length now is different, but the least radius of gyration remains the same. That evaluates to a slenderness ratio of 52. So example 1 there is outlined how we calculate slenderness ratios of our various struts. Exercise 1. A stanchion is made from 152 by 152 by 37 kilograms per meter universal column. The stanchion has a length of 2.5 meters. We've got to determine the slenderness ratio if the stanchion or strut is assumed. Part A, that both ends are fixed in direction, so in Castro both ends. That's fixed in translation and direction at both ends. And part B, one end is fixed and the other end is free. So one end fixed in translation and rotation and one completely free. The slenderness ratios are shown here in the bracket for reference. I'd encourage you to stop the presentation and attempt exercise 1. It's a very similar approach to that of example 1. I'll show you the full work solution on the following slides. So exercise 1, commencement of the solution here. From the question, the actual length of the column, L, is 2.5 meters. Converted that to millimeters here, it's 2,500 millimeters. The serial size is 152 millimeters by 152 by 37 kilograms per meter. So from our table in our notes, we can extract the least radius of gyration. Here's the table extracted from our notes for universal columns. So for a 152 by 152 by 37 designation, the least radius of gyration, about the y-axis always here, is 3.87 centimeters. So our K value is 3.87 centimeters converted to meters, 38.7 millimeters. Exercise 1, solution continued here. Just repeated the information from the previous slide for reference. So part A, the effective lengths, LE. From our tables, it's for a fixed at both ends strut, the effective length is 0.7 L, so 0.7 multiplied by the stanchion or column length here of 2,500 millimeters. The effective length is 1,750 millimeters. So evaluating our slenderness ratio, lambda, is the effective length divided by the least radius of gyration. Inserting the values, the slenderness ratio now is 45. Exercise 1, solution continued. Just repeating the information for reference. Part B, the effective lengths now, fully fixed one end and free the other end configuration. LE is twice the original length, so in this case that's 2 times the 2,500 millimeters, so 5,000 millimeter effective length here. Evaluating the slenderness ratio, that evaluates to 129. Let's now consider the entire selection process for calculating steel stanchions and struts. So the following procedure should be employed when selecting a standard rolled steel section as to withstand a specified load designated as P here. So initially we need to find A, the applied load, P, that the strut has to accommodate. Part B, we have to determine the type of end fix it is for the strut's structural arrangement. And C, we have to then calculate the effective length, LE, stating the value in millimeters. Selection process continued here. Let's consider the steps involved in the process. Step 1 here. We need to choose a trial column from our listing of universal columns, maybe initially using a section from the center of the table. We need to note from the table the cross-sectional area A, the least radius of gyration K, that's about the y-axis of bending. So the least radius of gyration occurs about the y-axis of bending, shown here. And we also need to note the flange thickness, capital T here. We will need to convert various values from the units stated in our standards for universal columns, etc., from centimeters squared to millimeters squared, and from centimeters to millimeters as required. Step 2, we have to calculate the slenderness ratio, the L upon K, of the trial section we're using. Selection process continued. So step 3. So from our appropriate table, we need to read off the maximum allowable compressive stress, labelled sigma, for the calculated slenderness ratio and flange thickness of our section. Here's an extract of the allowable compressive stress table reviewed earlier in the presentation. Step 4. We now need to calculate the safe axial load or force that the trial column can accommodate using the formula of the safe axial load. is the allowable compressive stress from step 3 above, multiplied by the cross-sectional area of our section, read from the appropriate table. In symbol form, safe axial load capital F is equal to the allowable stress sigma multiplied by the cross-sectional area of the section. In step 5, we now compare the safe axial load F with the applied load P given in the question, and if safe load F is less than or considerably greater than the applied load P, we then need to choose another trial section and we repeat the above selection procedure. So as you can see, the selection process requires iteration. We may need several trial sections before we decide upon the most appropriate section. Usually the appropriate section is found within 3 iterations. We will now consider a worked example to illustrate the above selection process. Let's consider an example 2 here. So a stanchion of length 10 meters is considered to have its ends fixed in direction and is required to accommodate an applied load of 500 kilonewtons. We're asked to determine the suitable universal steel column from standard section tables, which has the least mass. So here's our solution. To extract the information from the question, the compressive load applied in this case, P, is 500 kilonewtons. That's 500 times 10 to the 3 newtons. The actual column length, L, is 10 meters, or 10 times 10 to the 3 millimeters. And we're informed in the example to consider the ends of the stanchion to be fixed, so fixed in translation and rotation. So that means the effective length from our table is 0.7 of the actual lengths. So the effective length LE, 0.7 multiplied by L. So that evaluates to an effective length of 7,000 millimeters. Example 2, solution continued. This is our first trial. So I've chosen the trial column to be serial size 254 millimeters by 254 by 107 kilograms per meter. And that's just a decision that I've made. We need now to extract the various section values from the appropriate table in our notes or in the standards. So here's our universal column table again. I've highlighted here the values we need. So for a 254 by 254 by 107 kilograms per meter section, we can read the flange thickness T is 20.5 millimeters. The cross-sectional area is 136.6 centimeters squared. And the least radius of gyration is 6.57 centimeters. And here are the values stated. The area, 136.6 centimeters squared. Converting that into millimeters, got to multiply by 10 squared or multiplied by 100, so that's 136.6 times 10 to the 2 millimeters squared. The least radius of gyration K was 6.75 centimeters, so that's 65.7 millimeters. And the flange thickness T was 20.5 millimeters, this thickness here. That's the information extracted from our standard. Example 2, solution continued. Just repeated some of the properties from the previous slide here for reference. So now we have to calculate the slenderness ratio, lambda. That's the effective length, LE, which is 7,000 millimeters, divided by the least radius of gyration, 65.7 millimeters. So the slenderness ratio evaluates to 106.5. So step 3, we now need to determine the allowable stress from our appropriate table for the slenderness ratio stated above. So here's our table of allowable compressive stress values for our particular material. Our slenderness ratio is 106.5, so we're in between these two values here. We're obviously closer to the 105 than 110. Note that our flange thickness is 20.5 millimeters. So for a flange thickness capital T of 20.5 millimeters, that means we're in this column here. So 105 slenderness ratio, we have 129 newtons per millimeter squared allowable compressive stress, and at a slenderness ratio of 110, we have an allowable compressive stress of 121 newtons per millimeter squared. So I'm going to make an assumption here that the allowable stress will be 128 newtons per millimeter squared. That's my estimate. We are allowed to linearly interpolate between two values if we require to do so, but I'm just going to make an estimate here that at a slenderness ratio of 106, we're in the region of 128 newtons per millimeter squared. So the allowable stress here, sigma, 128 newtons per millimeter squared. That's the estimated value. So step 4, we now have to calculate the maximum load which the member can accommodate. So calculating F here, that's the maximum compressive stress above, multiplied by the cross-sectional area, listed here for reference. So inserting the values, the maximum load F is 1.75 meganewtons. That's 1.75 times 10 to the 6 newtons. Finally, for this first trial, we have to now compare the safe axial load F against the applied load P. So from our previous slide, the applied load P from the question was 500 times 10 to the 3 newtons, 500 kilonewtons. Of course, we could write that as 0.5 meganewtons. So dividing 1.75 meganewtons by 0.5 meganewtons, we find that the trial section is capable of carrying a load 3.5 times larger than required. So basically the section we chose is too big. So we're going to try a smaller section. So example 2, solution continued. I'm now going to show you the full work solutions of the trials, and I'll let you work through them at your own pace, accessing the appropriate information from the respective tables as required. So here's the solution for the second trial. This time the serial size chosen was a 203 mm by 203 by 60 kg per meter. For reference, here's example 2, trial 2, section properties associated with our second trial size, shown here in the table. The allowable stress this time was easy to determine. As the flange thickness was 14.2 millimeters, then we're in the first column here, and the slenderness ratio was exactly 135. So we can see that our allowable compressive stress is 89 newtons per millimeter squared. We can now use these values to calculate force F, the force the section can withstand. Essentially, we'll find that this second trial section still has a 35% larger load carrying capacity than that required. So again, we're going to try a smaller section. Example 2, solution continued. Here's the third trial. This time the serial size used is a 203 by 203 by 46 kilograms per meter section. Again, I'll let you work through this at your own pace, accessing the appropriate tables. So example 2, trial 3 here. Here's the third section chosen in our analysis. And again, we can read off the various properties from our universal column table here. Example 2, trial 3. As the thickness of the flange, capital T, is 11 millimeters from our previous table, we're again in the first column here of the allowable stresses. And because our slenderness ratio of 137 lies between the values of 135 and 140 in the table, I've again estimated the allowable stress for the flange at 87 newtons per millimeter squared. So again, we've got all the values we need now to calculate the maximum load F that the column can withstand. What we should find this time is that the section is only 2% larger in load carrying capacity than that required, so it's deemed satisfactory. So on the third iteration here, we've arrived at an appropriate section for this particular compression member. Exercise 2. A strut of length 8 meters with one end direction fixed and one end pin jointed is required to carry a compressive load of 750 kilonewtons. We're asked to select a suitable size universal steel column from our standard section tables, which has the least mass. The answer is shown here in the bracket for reference. I would encourage you to stop the presentation and attempt exercise 2, but I'll very briefly outline the full work solution on the following slides. Here's exercise 2, commencement of the solution. I will let you review this at your own pace. Just notice here that the effective length relates to a fully fixed one end and pin the other end strut configuration. Exercise 2, solution continued. Here's the first trial. Here's the designated serial size. Here's the information extracted from the appropriate table. Here's an extract of the universal column table for your reference. Exercise 2, solution continued. Here's the first trial. Here's an extract of the compressive stress table for your reference. Results in a section that can carry 40% larger load than required, so try a smaller section for trial 2. Exercise 2, solution continued. Second trial, new serial size here. Here's an extract of the universal column table for your reference. Here's an extract of the compressive stress table for your reference. This results in a section that carries a load 5% smaller than required, so that's not acceptable, so we need to try a larger size. Exercise 2, solution continued. Here's the third trial, serial size shown here. And this section can carry a load 15% larger than that required, so that's deemed acceptable here. So that's our final section. I will leave you with some tutorial questions to attempt at your own pace. Question 1 shown here. We're asked to determine the slenderness ratio shown here and calculate the maximum compressive load that a stanchion or a strut can accommodate. Answer shown here. Question 2. We're asked to determine a suitable I-section column capable of accommodating the load stated in the question. Just notice the load is stated in terms of ton here, so be careful with that. Answer is shown in the bracket here. Here's an extract of the universal column table for your reference. Here's an extract of the compressive stress table for your reference. Here's question 3. We're asked to design a stanchion using a standard section from our respective tables, which relates to a universal column capable of supporting a compressive load of 2 meganewtons. The answer for the serial size is shown in the bracket here. Question 4. We've got to calculate the maximum allowable compressive loads that the following stanchions can withstand. And we're given 3 different parameters here to consider, A, B, C. Notice that the stanchions are to be made from grade 43A steel that we've been referring to in this presentation, and we're also given a specific serial size to use. The answers for parts A, B and C are shown in the bracket here. And finally, question 5. We've got to determine a suitable size from our standard section tables for a grade 43 steel column, which has A, the minimum weight, minimum mass, and B, the smallest possible values of depth and breadth. Again, the answers are shown here in the bracket. I'd encourage you now to stop the presentation and attempt these questions. And finally, just for your interest, referring back to the platform we outlined at the beginning of the presentation and the design of the stanchions shown here, in actual fact, due to the configuration of attachment where the load is actually applied not directly through the center of the section as is assumed in the previous analysis, but actually is applied on the edge of the channel section due to the location of the two bolts in the channel flange. This strut was actually analysed as an eccentrically loaded strut, and there are separate analyses and separate formulae that you can use to analyse struts with eccentric loading or initial curvature. But that's beyond the scope of this presentation, so that's just a point of interest for you, should you experience that situation in practice. This slide just shows you the actual eccentric loading considered on our channel section. The P is applied on this flange here through the bolts. Here's the bibliography used to help generate this presentation, and once again I reiterate, I've used superseded standards or codes of practice in this particular presentation as I'm just trying to outline the process involved in sizing compression members. If you are sizing components for industry, then please ensure you refer to the appropriate and up-to-date standards. I hope this has been of some interest to you, and thank you for viewing.